right, so this lesson is all about logarithmic functions and writing equations of logarithmic functions as it relates to exponential functions. And it says here by definition that the logarithmic function is the inverse of an exponential function. So logarithmic functions, I'm just going to make that note up here, inverse of exponential. And if you remember back when we were talking about inverses earlier in chapter 5, remember with inverses, all we do is interchange the x and y's. We flip the domain for the original function and it becomes the range of the inverse function, and the same thing with the range of the original becomes the domain of the inverse function. And we're going to talk about that a little bit more when we get to graphing. And it says here that the logarithmic function to base a, where a is greater than 0 and a does not equal 1, is denoted by this notation. And I read this as, log base a of x is y, or y is the logarithm to the base a of x. All right, so it means the same thing. But logarithmic functions and exponential functions can be rewritten to look, they can be converted to each other. Just like if I have x plus a is y, I could also write this as x equals y minus a. So here I have an addition problem, and the inverse I know is a subtraction problem. All right, so it's kind of like the same thing that we're doing here with logs and exponential sentences. So just looking at our first example here with exponential sentences, it says that y equals log base 3 of x. So we're going to write this as an exponential sentence. So the base is going to be the base of the exponential equation. And I kind of work in a circle, backwards and around. So I'm going to start with my base. Y now becomes the exponent, and x is the answer. All right, so this works for anything in terms of log equations. So I start with the base, 3 to the 4th power equals 81. Okay, and we know 3 to the 4th power is 81. How about 5 to the y power equals x? Or 5 to the negative 1st power equals 1/5. So these are all logarithmic sentences that we've written as exponential sentences. Okay, so if I remember y equals log a of x, a is my base, this becomes my exponent, and this becomes the answer. All right, so now in this section down here, I'm going to go the opposite way. I'm going to take 1.2 to the 3rd power equals m. All right, so if I think about this, my base is 1.2. Okay, the base in the logarithm and the base in the exponent are the same number. So I have log, my base is 1.2 of m equals 3. Okay, log 1.2 of m equals 3. And I can do that circle thing and check 1.2 to the third power equals m. Okay, and that's what I started with. Here I have log base e of 9 equals, I think that's a b, it's very small. So e to the b power equals 9. Here's log base a of 24 equals my exponent. The answer to the logarithm is always going to be the exponent. Okay, so a to the fourth power is 24. So here in example 3, it says to change log expressions to exponential expressions. All right, so I'm just going to write this as an exponential sentence, just like I did up here. All right, so I start with a to the fifth power equals 4. E is my base to the negative third power equals b, and 3 to the c power equals 5. Okay, so it's very important that we're able to convert between exponential and logarithmic equations or functions. All right, so on the next part, it asks us to evaluate some of these logarithms. So the first thing we're going to do is write this as an exponential sentence. So because I don't have an equation here, I'm just going to make all of these equal x. And I'm going to write the exponential sentence. So my base is 2 to the x power is 16. And if I just do some mental math here, I know 16 is a power of 2. And if I count how many 2's it multiplies to be 16, that's 2 times 2 times 2 times 2. So 2 to the fourth power is 16, so x is 4. Next one, 3 to the x power is 1 over 27. Now 1 over 27 is the same as 3 to the negative third power. So if I have 3 to the x power, and that equals 3 to the negative third power, x must be negative 3. So the log of base 3 of 120 over 27 is negative 3. This next one says e to the x power equals 1. And we know we're finding the exponent of something that gives us 1. Any number to the 0 power is always 1, so x must equal 0. All right, so the domain of a log function, and if we think of exponential functions, an exponential function looked like this. So remember, the domain was all numbers greater than 0. And the range actually, it could be, sorry, I'm thinking backwards already. The domain actually is all real numbers, okay, because it can go into negative x values. But the range is always y is greater than 0. Now for a logarithmic function, if I flip this over that y equals x line, this is what it looks like. So in this case, my domain has to be all the numbers greater than 0, and my range can be all real numbers. Y is any real number. So just notice how the domain of the original function becomes the range of the inverse function, and likewise with the range to the domain. All right, so here it's asking us to find, and I just kind of summarize this because sometimes I think some of this technical stuff here is kind of hard to follow. But basically what we said here for our domain is the x's, or the part of the equation with the x, has to be greater than 0. So if I look at this part with the x, okay, this x plus 3 has to be greater than 0. And if I subtract 3, my x values are going to be greater than -3, which kind of makes sense because this is a shift to the left. So if my original range was greater than 0, if I shift it to the left 3 units, my new domain is x is greater than -3. All right, so here let's look at this next part with the x in it. So here my x squared has to be greater than 0. Okay, we know that x cannot equal 0. So here x is always going to be greater than 0. So x is always going to be positive. Okay, when you square something, you're always going to get a positive number. And this last part, this is telling me that I'm shifting up or down. So that really affects my range, which is all real numbers anyway. So I'm still just looking for my domain as 2x minus 5 has to be greater than 0. So I'm going to add 5, so 2x is greater than 5, and divide by 2, so x must be greater than 5/2, and that would be my domain. So all of these, my domain, set the x part of the equation to be greater than 0, and then just solve for x. That's the simple way of working with that one. All right, so on the next page, most of this is just FYI stuff, and it gives us a good example of if this is an exponential function, y equals a to the x, it gives us the inverse function as a graph being reflected over that y equals x line. So this point of 1 comma a becomes the point a comma 1, okay, and it's just reflected over that line. In an exponential function and a parent function, no matter what the base is, anytime you have a 0 power for x, if x is 0, y is going to be 1, and the reverse is true for a logarithmic function. The point 1, 0 is always on the parent function of a logarithmic function. Okay, and this is -1 comma 1 over a, and this is 1 over a and -1. So these are just reflected over that axis. Okay, same thing over here. Here's a exponential function. Okay, this time my a value is a fraction. Okay, so my base is a fraction. So if I plug in an exponent of -1, I'm getting a very large number because I'm doing the reciprocal and then my y value is just 1 over a. Okay. Here's the point, over 0, up 1, same as on this side. Okay. So this is a exponential equation where my base is between 0 and 1, and then this would be the logarithm function as an inverse reflected over the y equals x line. You can see where these points kind of coordinate with each other. Right here. All right, so what should we know about logarithmic graphs? First of all, the domain is the set of positive real numbers, and the range is the set of all real numbers. Number 2, the x-intercept of the graph is 1, and there is no y-intercept. Okay. The x-axis, or the y-axis, which is the line x equals 0, is a vertical asymptote of the graph. So if I look back up here, I have a vertical asymptote here. Remember, I had a horizontal asymptote with an exponential function. This exponential function came close to the x-axis without touching or crossing, and if I flip this, it's going to come close to the y-axis without touching or crossing. Okay, so I have a vertical asymptote opposed to a horizontal. And the graph contains these points always. Whatever the base is A. So I always have the point 1, 0. My base is whatever the base is and 1. And then 1 over a and negative 1. All right, and we're going to look at those points in a little bit. Now, when we specifically talk about the value of e as my base, e to the x power, remember that would be the same as 2.72-ish to the x power. That would be the exponential equation. But when we're talking about the log of this, we use this notation ln, and ln is a French word which means logarithmic naturel. Okay, and in English we call this the natural log. Okay, and this only works if our base is e. All right, and this is just the graph down here of e to the x power, and the inverse or the natural log function down here. And remember, we're just changing the x and y values on these. All right, so now let's graph some exponent or some logarithmic functions. And wow, there's a few ways that we can do this. I'm going to use a table, and I'm first going to write this equation as an exponential sentence because I think we understand the concept of exponents better than we do the concept of logarithms. So first of all, I need to write this as exponential. I need to identify the base. Now this log doesn't have a base written down, so it's assumed that this is log base 10 of x. Okay, so if there's no base, assume that the base is 10. It's kind of like if we have a variable and we want to know what the coefficient of that variable is. If there's no number there shown, we assume that the coefficient is 1. And that's kind of the thinking behind this. It's the common base, and it's what we use in our counting system, and that's why they call this the common base is base 10. All right, so if I were to write this as an exponential sentence, I would have 10 to the y power equals x. Now I'm going to make a table, and on the opposite page we had some points that should be on our graphs for logarithm functions. I'm going to say, and this is an x and y table, let's automatically choose values like -1 for y, 0, and then +1. Now remember, we're usually choosing values for x, but these are the values that I'm going to plug into my equation to find x. So if I plug in -1 here, I have 10 to the negative first power, which is 1 over 10. If I go to a y value of 0, I have 10 to the 0 power is 1, so x would be 1. And if I plug in a 1 here, 10 to the first power would give me 10. Now I'm going to plot these values. And I'm making this kind of long because I know I have a long x-axis. I'm going to go up to 10. Okay, 1, 2, 1, 2. If I need more points to determine what the direction of this is going to be, I can always choose -2 and +2 to put in there for y. So let's plot this point. My x value is 1/10, so that's very close to my y-axis, and my y value is -1, so that's about right here. Then I have over 1 up 0, and remember the x-intercept of 1 is in our logarithm graph unless it's being shifted. Okay. And then I have over 10 up 1. So here's 10 up 1. So my graph of this is looking like this. Remember, it doesn't hit that x-axis because it is a vertical asymptote, or the y-axis is a vertical asymptote. All right, so there's my graph of log of x. All right, this next one. This one gave me some problems when I was practicing it. Now, if I remember, natural log, this ln, only works if I have a base of an e. So my base is e, and I'm going to do some flipping here. So I'm going to move this negative over here. So I'm going to multiply both sides by -1. So this is -y equals ln e x minus 2. So now I'm going to write my exponential sentence. Okay, so I just did this to make it a little bit easier for us with this negative. I'm going to have e to the -y equals x minus 2. Okay, e to the -y equals x minus 2. And if we remember, this negative here, if I think about the transformations, the negative is going to be a flip down. And this is going to be a shift, and it's going to go not in the negative direction, it's going to go right 2. Okay, so we should think about that when I'm doing my graph. All right, so first thing, let's draw our graph. And I know that my vertical asymptote isn't going to be the y-axis. I'm going to shift it over to the right 2 units. So here's my vertical asymptote. All right, so let's get some points that we're going to plot on this. So we'll have x and y. And remember, I want you to use these designated y values. So if y is -1, y is 0, and y is +1. And if we need something else in the meantime, we can add whatever we need. So I'm going to plug in y. In this case, y is -1. So I'm going to go to the opposite of y. So this is the opposite of -1 is +1. And it might be easier if I just solve this for x and say that to find x, I'm going to do e to the -y, and then I'm going to add 2 over here. Okay, so that just means all of our calculations, when we plug it in, we add 2 at the end, and that will tell us what x is. So the -1 exponent, the opposite is 1, so I'm going to have e to the first power, and then I'm going to add 2 to that. All right, so remember, e is 2.72. So if I add 2 to that, that's going to be 4.72. If I have 0, the opposite of 0 is 0. So e to the 0 power is 1, plus 2 is 3. And if I put a 1 here, I'm going to have e to the -1st power, and then add 2. So e to the -1st power, is, and I'm just looking at it on my handy dandy calculator, e to the -1st power is 0.367. And then if I add 2 to that, I'm going to get 2.36 or 2.4. All right, so let's plot these. So my x value, here's my y values. My x value is 4.72. Here's 1, 2, 3, 4, 5. 4.72 is close to 5, and I'm going down 1 for -1 for y. Then I have over 3 up 0. So now my x-intercept isn't at 1, it's shifted over 2 units to 3. And then this tells me I have the x value of 2.4, 2.4 up 1. So my graph looks something like that. All right, let's move on to C. All right, so first of all, notice how in this part and on this part, my x -2 and my x -1 is in parentheses. In this case, I kept it together with x. On this case, I'm going to move it over to the other side before I do my exponential sentence. Okay, so if I just look at what this means, this is going to mean a shift, and it's going to go down 1. Okay, so keeping that in mind. So if I move the y, or the -1 over here, I have y plus 1 equals log base 3 of x. So now I'm going to write the exponential sentence of 3 to the y plus 1 equals x. And let's make that table. So if I do -1, 0, and +1, plug in -1 here, -1 plus 1 is 0, and 3 to the 0 power would be 1. If I plug in 0, 0 plus 1 is 1, so 3 to the first power is 3. And plug in 1 for y, 1 plus 1 is 2, 3 squared is 9. Okay, so just on my graph, so I have the point, I'm going to go backwards, over 9 up 1, over 3 up 0, and over 1 negative 1. Okay, over 1 negative 1. All right, so it's going to look a lot like this. Okay, last one. My x is grouped together with this minus 1, so I'm not going to separate it. I have 2 to the y power equals x minus 1. Okay, now I'm going to move this over. And if we think about this, this should be a shift to the right 1 unit. Okay, so I'm going to add 1, 2 to the y plus 1 equals x. So now I'll make my table of x and y values. Negative 1, 0, and positive 1. So I'm looking at this equation. I'm plugging negative 1 in for y, so that would give me 1/2. Plus 1 would be 1.5. Okay, so 1/2 plus 1 is 1.5. 0, 2 to the 0 power is 1. 1 plus 1 is 2. And plug in 1, 2 to the first power is 2, plus 1 is 3. And I have over 1.5, down 1, over 2, up 0, and over 3, up 1. Okay, it almost looks linear, but we know I should have, I'm moving to the right one, I should have this asymptote here. And that's what that one looks like. All right, so we'll do some more practice with this, but again, I think it is much easier for us to think in terms of exponential sentences and kind of pick the values of y instead of x. And if we stick with these particular values of y, I think we can get a good visual of what our graph should look like.